Welcome back everyone to our second video here in section number 4. Here we're going to be interested in trig limits, right? In our first video, as we were taking the derivative, as we were figuring out the rate of change for sine, we came across some interesting trig limits. This sine of x over x, as x was going to 0, and this cosine of x minus 1 over x, as x was going to 0. I know technically we used h's, but now thinking about them as limits, it's nice to use x so that we can go ahead and graph these and verify these things. And the claim in our first video was that this limit was equal to 1, and this limit was equal to 0. But nowadays, right, we have all of this great graphing technology, so we can go ahead and verify this. So if I go ahead and bring up Desmos, notice I went ahead and I graphed sine of x over x. First of all, if you were to plug in 0 everywhere you saw an x, you would get 0 over 0, right? That wouldn't make any sense. However, right, so you can't plug in 0, but you can talk about the limit as x goes to 0. And when you look at this as you approach from either the left or as you approach from the right, it seems like it's getting closer and closer to this y value of 1, right? Height 1. And so, okay, we would propose that, yeah, that this function is heading towards 1 as x goes to 0. Likewise, I went ahead and graphed this cosine of x minus 1 all over x. And we can see as we approach from the left and as we approach from the right, it's getting closer and closer to the y value 0. And so therefore, looking at these graphs, we would say, yeah, it makes sense that this limit is 1 and this limit is 0, right? But many, many years before we had all this great graphing technology with the calculators and computers and stuff like this, this limit here was still a well-known fact. And the way that mathematicians solve this sort of limit is by using, right, a combination of algebra and geometry. And the proof for this is really beautiful, so I would like to demonstrate this proof, right, how they figured this out years before we had any of these great graphing capabilities. All right, so my proof here, for those mathematicians watching, I'm going to do a proof for x greater than 0. So this is technically proving the right-sided limit. Again, as x is greater than 0, you could also do a very similar proof for x less than 0, and then you'd have the right side and the left-sided limit, and therefore the two-sided limit would exist. Okay. In order to do this, right, I told you that we're going to need to use algebra and geometry. So let's go ahead and review a few geometry facts. So let's go ahead and recall. And the first geometry fact that I would like to recall is for an area of a triangle. So area of triangle, and that's going to be 1/2 times the base times the height. So this one you probably remember. We use this quite a lot. One, however, that I find, significantly fewer people remember is for an area of a sector. And this will come up in the proof, so I want to write down right now an area of a sector. What is a sector? Well, a sector is a piece of a circle. So if I have my full circle here, a sector would be just a piece of it. So I can go ahead and take a piece. And in order to get the area formula for a sector, you want to know what is the radius of the circle. And you also want to know how big is your sector. And that's going to be given by our theta value, right? What is this angle for this sector? So that right there is a sector. Let me maybe even highlight it. I'll use purple, why not? But that right there is a sector. And the area formula for a sector goes 1/2 times the theta value, right? What is your angle? Times the radius squared, right? So this kind of even looks like the area formula for a circle, right? Pi r squared. That's where the r squared comes from. But then in this case, we're only doing a piece instead of the entire 2 pi, right? 2 pi would be the entire circle all the way around. Okay, so we need those two area formulas for our upcoming proof. And if this looks familiar, the sine of x over x, that's very great, right? Because we actually brought this up in 1.6. This proof is going to require the squeeze theorem, right? So we brought up the squeeze theorem in 1.6, and I brought up this one. This is another application of the squeeze theorem. So we're going to go ahead and try to squeeze this thing between a couple of other functions. And so it's not at all obvious what we're going to actually squeeze this between. And so this is where kind of these areas of triangles and sectors are going to help us. So let me go ahead and I'm going to draw some unit circles here. So I'm going to draw a unit circle. And so we have our unit circle, and in fact, we're only going to need a piece of it. So I want to just focus in on the piece that we need. So I'm going to do the unit circle that's in the first quadrant. And now we're going to be interested in sine of x. That's a big part of this function here, sine of x over x. So let me go ahead and draw a point on the unit circle. And this maybe has angle x. All right. So again, I'm going to be using the squeeze theorem, so I want to squeeze something in between these things. So actually, let me draw a few more unit circles using the magic of technology. There we are. So you may want to pause the video, right, and draw out these 3 copies of my unit circle with an angle x, because this is what we're going to need for this next part of the theorem. So again, I would like to squeeze this sine of x over x between a couple of other functions. It's not obvious at all what those other functions are at this point, but luckily this geometry is going to help us. So I'm going to draw 3 shapes. The first one here is a triangle. So let me go ahead. We use green. I'm going to add this line right here. I'm going to drop this perpendicular so it's a nice right triangle here. The second one is going to be the sector. So I'm just going to leave this one alone and look at the sector. In fact, let me go ahead and maybe start highlighting these. So this is the first shape that I want to think about. The second one is this sector right here. There we go. And then the third one is going to be, it's a little confusing, right? So I'm going to go ahead and take this point right here and raise up a perpendicular. So this is a nice 90-degree angle. And then I'm going to extend this line here until it crosses. And this is going to give me a third triangle. And so the nice thing about these 3 shapes is that for really any x value, any positive x value, we have that the area of this green triangle, notice this green triangle kind of fits inside of this sector. So the area of it, of this green triangle, is going to be less than or equal to the area of this purple sector. So let me go ahead and draw a little sector here, color it purple. And that area is going to be less than or equal to, notice, well, this orange triangle is even bigger than the purple one. So its area is going to be even bigger. So area of the orange triangle. And now you can notice that we're getting some inequalities here, that this is starting to set up that squeeze theorem that I promised you. So now the big question is, okay, I need to use these area formulas, but in order to do that, right, I need to know like what is the base, what is the height, stuff like that. Area of a sector, another area of a triangle. So let me go ahead and write some area formulas here. So, okay, in this case, we know that the height of this point, aka this value right here, is going to be sine of x, because it's on the unit circle. So the height of this point is given by sine of the angle x. Likewise, the x value of this point, right, kind of left and right, this is going to be given by cosine of x. So this area of the first triangle is going to be 1/2 the base times the height. And that's going to be less than or equal to the area of the sector. So the area of the sector, well, using this formula over here, that's 1/2. The theta value here, what is your angle? Well, that's given by x in this case. And then finally, what is the radius? Well, we have the radius of the unit circle is 1. So this is going to be 1 squared. All right. And finally, the area of the orange triangle. Well, we're going to have 1/2. The base here, well, notice the base is the entire length of this unit circle, right? It is one of these radiuses of the unit circle. So that's going to be 1. So all we need is the height in this case. And this takes a minute to argue out, but again, because this is length 1 right here, we know tangent is supposed to be opposite over adjacent. Opposite over adjacent. Well, if your adjacent is 1, well, this then has to be all of the tangent. right? Tangent is opposite over adjacent, so that's tan of x over 1. Perfect. So this is tangent. Okay, so now let's go ahead and start manipulating this. Again, I want to say something about my sine of x over x. So let's go ahead and start doing a few things. Maybe the first thing I'd like to do is multiply through by 2. Notice there's a 1/2, a 1/2, and a 1/2. So if I multiply through by 2, and now at this point, let me go ahead and write, instead of tangent, sine of x over cosine of x. Now, let me go ahead and divide through by sine of x on all sides. So if I divide this first one by sine of x, it just goes away and I get cosine of x. Here I would have x divided by sine of x. And here I would have, well, if I divided by sine of x, this would just be 1 over cosine of x. And now I'm ready to go ahead and apply the squeeze theorem. Remember, I'm interested as x goes to 0. So as x goes to 0, this limit of the left-hand side is going to go to, well, cosine of 0, which is 1. On the right-hand side, right, our big function, again, as x goes to 0, I'm going to have 1 over 1, right? Cosine of 0 being 1. Well, that's just the same thing as 1. So therefore, by the squeeze theorem, we know that the middle function must also go to 1. So by the squeeze theorem, the limit of x going to 0 of x over sine of x is equal to 1. So this is close to what we wanted, but notice we have it kind of flipped. I have the x on top and the sine of x on bottom. How do I fix that? Well, I need to do the reciprocal, right? So if I do the reciprocal, I would get something with the sine of x over x. And this would go to, well, the reciprocal of 1. That would be 1 over 1, right? That was one of these nice rules for limits that we can apply here. Well, again, 1 over 1 is just going to be 1. So this is the nice formal proof that the limit as x goes to 0 of sine of x over x equals 1. Notice we don't need, these great graphing technologies and stuff like this. This is something that they were able to figure out many, many years ago. Again, thanks to algebra and geometry. All right, so this will lead to a whole bunch of limit questions that are interesting in their own right. So I would like to upgrade this theorem a little bit to what if you just don't have just regular old x inside, but you have some other function, f of x. And the claim is so long as whatever's inside of your sign matches what's in the denominator, and that these things are going to 0. So the function should be going to 0. So again, it's going to be kind of like a sine of 0 over 0 situation. Then this limit will still evaluate out to 1. And likewise, if you take the reciprocal of these things, right, this will also evaluate out to 1 over 1, the reciprocal, which 1 over 1 is the same thing as 1. So this enables us to do more complicated limit problems. Let's go ahead and see this in action. So here's an example. Again, we don't have just regular old sine of x in here. We have sine of 5x. So I'm technically using this. In order for this to work, I need whatever's inside of the sign to match what's in the denominator. So I'm going to go ahead and rewrite this. I'm going to do the limit as x goes to 0 of sine of 5x, and I'm going to divide this by 5x. Now I just changed some things, right? First of all, I can't forget that I really have a 3 down here. So I'm going to go ahead and move this 3 off to the side here. And I made a 5 appear in the denominator. If you're going to make a 5 appear in the denominator, well, in order to make this mathematically valid, you should also make a 5 appear in the numerator. Then this is just a fancy way of multiplying by 1. So now, notice that I have all these pieces still, right? I didn't forget about the 3. I just moved it off to the side, right? You can multiply in any order. And since I made a 5 appear in the denominator, I also make a 5 appear in the numerator, so this is just a fancy way of multiplying by 1. All right, now, as x goes to 0, notice what's inside of the sign matches exactly what's in its denominator now. So therefore, this is going to go to 1. And the 5/3, well, this doesn't have any x's, right? So this is just a constant. So this is 5/3. So 1 times 5/3 is 5/3. And there is our final answer for this problem. So you can see that we can now do more types of limits. Let's try one more here. Find the limit as t goes to 0 for tangent of 2t squared over 4t. So let me go ahead and rewrite this. Notice I don't have any limit rules for tangent. So I'm going to go ahead and rewrite this as sine of 2t squared divided by cosine of 2t squared. And then let me go ahead and move this 4t off to the side here. So I'm going to go ahead and write this 1 over 4t. Okay. This is essentially, instead of dividing by 4t, I'm multiplying by its reciprocal, 1 over 4t. Okay, so now let me go ahead and rearrange things a little bit. The limit as t goes to 0. All right, so I'm going to have sine of 2t squared. And in order to apply this theorem up here, I would like what's inside of the sine to perfectly match in the denominator. So I'm going to go ahead and make this divided by 2t squared. Now, if I'm going to make a 2t squared appear in the denominator, I should also have it appear in the numerator, so that this is just a fancy way of multiplying by 1. So I'm going to go ahead and multiply by 2t squared as well. All right, and then I still have this cosine that I can't forget about. It's in the denominator. And I have this division by 4t. Actually, let's go ahead and combine that right here. So this, I'm going to put the 4t in the denominator here. They're kind of like terms, right? All right, so now as t is going to 0, we're going to have this is heading towards 1. Likewise here, we would have 1 over cosine of 0. Well, 1 over cosine of 0 is 1, right? Really 1 over 1, which would evaluate out to 1. And now in this case, well, you can notice there's a little bit of cancellation here. I have 2 t's on top and 1 t on bottom. And then I have a 2 up here and a 4 down here. And so as t goes to 0 here, well, notice I have 1 t in the numerator left. So this is going to be going to 0 over 2. Well, 0 over 2, that's just 0. So when I multiply all these things together, 1 times 0 times 1, I'm going to get out 0. So remember, this is technically using like a product rule for limits, right? Remember, the product rule for limits was exactly what you wanted. You could just take the limit of each one of these pieces and then multiply it together. The product rule for derivatives is much more complicated, as we've seen. But the product rule for limits is really, really nice, right? You just take the limit of each one of these pieces, then you multiply it together, and that gives you the final result. So in this case, we would have the limit is equal to 0. The limit of tangent of 2t squared over 4t. That goes to 0. All right, that is it for section number 4. We've done lots of things right now with our derivatives. We've been interested in this instantaneous rate of change. We've done product rules and quotient rules. We now know how to take the derivative of trigonometric functions. Next time, we're going to be doing something called the chain rule, which will help us take the derivative of compositions of functions. All right, I'll see you then.